Good morning. Today I'm going to discuss the topic synchronous counters. But unlike asynchronous counters, synchronous in a synchronous counter, every flip flop is activated by or it is triggered by a common clock. Common clock. That is the difference between synchronous counter and asynchronous counter. In asynchronous counter, only the first flip flop is given a clock, and then the output of one flip flop is given as the input or clock input of the next flip flop, and like that. Here, same clock is applied to all flip flops. Same clock is applied. Now we are going to discuss how the design of a counter can be done uh, using synchronous counters. So these are the steps to be followed. Uh, Find the number of flip flops required. For example, if it is a 3-bit counter, then you need 3 flip flops. If it is a 2-bit counter, you need 2 flip flops. Like that. If you have a 4-bit counter, then you need 4 flip flops. And find the number of flip flops and decide upon what is the what is the type of flip flop we are going to use, whether it is J, K, D, T, etc. And that also you have to decide. Then construct the excitation table of the flip flop. Excitation table of the flip flop in the sense, we'll discuss that the excitation table of the flip flop is like this. That means if the current state is 0 and the next input is 0, then what should be the value of J and K? That means J should be 0 and the value of K is not well, it can be either 0 and 1. That means it is a don't care condition. If you are switching from 0 to 1, if it has to switch from 0 to 1, if the output has to switch from 0 to 1, you have to make this 1x. That means J has to be 1 and x is a don't care. 1 to 0 it is x1 and 1 to 1 it is x0. And that is the excitation table of the flip flop. And draw the state diagram of excitation table and flip flop. Draw the state diagram and excitation table for this is the state diagram. This is an example. I will show you how this is done. Use the K-map to obtain simplified expression for each input of flip flops and complete the logic diagrams. So we are going to have a design of a 2-bit synchronous subcounter. That means 2-bit synchronous subcounter means 2 bits 0 0 0 1 1 0 1 1, again 0 0 0 1 1 0 1 1, 0 0 1 0 0 0 1 1 0 1 1, like that. So this is the state diagram for that. So initially the first step is, this is a mod 4 up counter, modulo 4 up counter. That means this is after 0 0 it is moving to, or the next state is 0 1 1 0 and 1 1. Design a 2-bit synchronous up counter. Now as it is a 2-bit counter, you need only 2 flip flops. Number of flip flops required is 2, and for this I am going to use, as it is an up counter, we are going to use negative edge triggered flip flop. We are going to use negative edge triggered flip flop, and the flip flop used is JK flip flop. And as I told you earlier, this is the excitation table of JK flip flop. That means if the current state is 0, then next state has to be 0. The input has to be 0x. So if the 0 to 1, that means previous value of q is 0. Next state has to be 1. Then you have to give 1x and like that. Okay. So this is step 3. Step is start, draw the state diagram and excitation table of flip flop. This is the state diagram: 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1, like that. Or 0 1 2 3, then it is coming back to 0 1 2 3, and this has to be repeated. Okay. So now that is about the state diagram, and this is the excitation table. That means if the present state, if you have 2 flip flops, see, if you have two flip-flops. I'm going to draw two flip-flops. This is flip-flop number 1, F of 1, and this is F 0. Flip-flop 0. This is JK flip-flop 0. 0 and 1. Now, if Q1 is the output of flip-flop 1, this is Q1 and this is Q0, and this is J1, this is K1, this is J2 and this is K2, and this is Q0 bar and this is Q1 bar. Now, a common clock is applied here. That means here, as this is a negative edge triggered flip flop, again here, that means this is the clock and clock is applied there. Now, if Q1 is 0 and Q0 is 0, suppose that Q1 and Q0 are 0 and 0, the next state is 0, 1. That means if Q1 and Q0 are 0 and 1, that means after 0, 0, the next state is 0, 1. That means it has to switch from 0 to 0 and 0 to 1. That means, see, this 0 has to be converted to this 0 and this has to be converted to 1. That means the current state of the first flip flop is Q1 0 and next state also is 0, and current state of Q0 is 0 and the next state is 1. That means this flip flop, that means after 0, 0, this flip flop has to stay the same state and the next flip flop has to be converted to 1. That means here initially the output is 0 and that has to change to 1, and here it is 0 and it is switching to 0. Okay, that means 0 to 0 and 0 to 1. So if it has to switch from 0 to 0, then what does this? The J and K input should be 0. For 0 to 0 transition, the J and K value should be 0x. So we have written here 0x. This J1 and K1 has to be 0 and x if you have to stay in the same state. That means 0 to 0 transition, J1 and K1 has to be 0 and x. And for 0 to 1 transition, what is the say? 0 to 1 transition is 1x. So here you have a 0 to 1 transition, that is why we have put here 1x. Okay, 1x. Now, previous state is, present state is 0, 0 and the next state is 0, 1. Now, for the next state, that means now 0, 0, 0, 1. Now, the present state is 0, 1. Now it is 0, 1. Okay. Now, the next state is 0, 1 has to be converted to 1, 0. That means this has to be converted to 1 and this has to be converted to 0. That means the next state is, here there is a 0 to 1 transition and here there is 1 to 0 transition. That means initially 0, 0, then 0, 1, now 1, 0. So for flip flop, first flip flop, you should have a transition from 0 to 1. For 0 to 1 transition, you have to put 1x. That means here 0 to 1 transition, you have put 1x. And here there is 1 to 0 transition. That means see, here Q0 is 1 and here it is 0. 1 to 0 transition. Then this is not J2 and K2. This is actually J0 and K0. This is J0 and K0. Okay. Now, this J0 and K0 value should be, that means transition is from 1 to 0. if you want 1 to 0 transition, then x1. That is why you have x1. Okay. Then now 0 0 0 1 1 0. Next is here 1 to 1 transition, and here 0 to 1 transition. If you want 1 to 1 transition, then that should be x0. That means here, see, here we have 1 to 1 transition, and here there is a 0 to 1 transition. For 1 to 1 transition, the excitation table shows the value of J1 and K1 should be x and 0. And for 0 to 1 transition, the value is 1x. See the excitation table. Now, once you did it, now the next step is this one is converted to 0, and this has to be converted to 0. That means 1 1 to 0 0. That is the transition 1 1 to 0 0. Okay. Then 1 to 0 transition. What is the x1? Here also 1 to 0 transition x1. That is why x1 x1. Now you have the truth table for J1, K1, J0 and K0. J1, K1, J0 and K0. Now, if Q1 and Q0 are 0 and 0, the value of J1 should be 0 and K1 should be X. Now, if the value of Q1 and Q0 are 0 and 1, now the J1, the value of J1 and K1 should be this, and value of J0 and K0 should be this. Now, using Karnaugh map, that means here this J1, K1, J0 and K0 can be, that means using Q1 and Q0, we are going to have a combination circuit which is developing J1, K1, J0 and K0. That means once you have the value of Q1 and Q0, you can easily find out what should be the value of J1, what should be the value of K1, what is the value of J0 and K0. Okay, once you have that value of Q1 and Q0, you can easily develop J1, K1, J0 and K0 using Karnaugh map. So here we have only 2 bits, that is why 2 by 2 Karnaugh map. Then here this is Q1 and Q0. Then what is this is J1. So 0 0 it is 0, 0 0 it is 0, 0 1 is 1, and then 1 0 is 1, and 1 1 is 0. No, 1 0 is x, and 1 0 1 1 is x. That is why you have xx. Now I am going to group this. That means 1 and x. Then what is this? J1 is equal to that means this has gone. That means Q1. This is Q1. This is Q1. Q1 has gone. Q0. That means here this is the column representing Q0, and that is why J1 is equal to Q0. Okay, J1 is equal to Q0. Now, using this Karnaugh map, we have developed, or we have entered the details of Karnaugh map for K1, and using this again, I am going to have a grouping like this, and now K1 is equal to, what is this? K1 again is J0, K1 is, see, that also is Q0. Now, this is 1x and 1x. Now, I am going to group this. That means everything has gone. That means J0 is 1, and what is the value of K0? Here this is also everything. That means J0 is equal to 1 and K0 equal to 1. That means here J1 is equal to Q0, K1 is equal to Q0, J1 is equal to Q0, K1 is equal to Q0, J0 equal to 1 and K0 equal to 1. That means here, see, I am going to have, this is J0 and K0 should be 1. Here I am going to provide 1 here. J0 and K0 are 1. Here 1. And what is the value? J1 and K1. J1 and K1 are Q0s. So J1, that means this Q0 is given back to J1 and K1. So this is the counter. This is the 2-bit up counter. One more example I will show you. That means a 3-bit counter. How that can be developed. That we will discuss later.